All right, so we'll go ahead and get started. I don't know if anyone noticed, but SolidWorks is back up again. I went and stripped it off to this machine and put the old one back on. So I get to redo that again. Anyway, hopefully that's good for a year now. Yeah.
I actually like that focus today, so are you able to just go back in work? That's the problem because I did join SolidWorks this morning and then try using CFX on the lab work.
You might try. So how far did it get? Did it just not want to import, or?
Yeah, so I'll use the SolidWorks part. I'll try to generate it.
Okay, we'll actually go through part of 5 and let me know what point it's failing at. So there's 2 possible things. One is it might just not recognize the solid part, in which case you could try a parasolid. The problem you're having with SolidWorks being gone completely was that if you installed ANSYS with the CAD support, the add-on for it, if it couldn't reach SolidWorks, it would hang for a ridiculously long time, like half an hour, and then it would pop up with something saying it timed out. And there was no way to get around it. I tried every geometry type I could find that was not associated with SolidWorks in any way. The same problem. So then ANSYS was like broken. If you didn't have that CAD add-on installed, probably it would have worked. I never realized there could be a downside to having that add-on. So maybe I'll rethink that next time and just deal with solid parts. If it's just not wanting to read the solid part, could be there's no CAD support in that particular install of ANSYS. I also don't know if there's a generational thing. If the old ANSYS was pointed to a particular version of SolidWorks and the new one maybe it doesn't see. I don't know. So anyway, we'll give it try some things, and if it is really broken, then we're gonna have to try to get ITACs to work on the machines. The guy is like really unbelievably pissed off. He's an angry individual. And if you see him working on a machine, maybe don't log him out because when he's on remotely, because he apparently takes revenge, I guess.
Oh yeah, he wiped my entire drive.
So. Yeah. Well, there's ITACs. All right, so we're not going to do too much new material today. We'll actually look at homework 5 a bit, but before we do that, I had a couple of people, probably most people understand this, but a couple of people asking questions in email about the finite wing theory. And they start with a picture in the book, like finite wing, got down circulation, results in these horseshoe vortices. And the question they were asking is, okay, these are tip vortices. So then how do we move to a case where, say, we have now different vortices that are shed, and these are not at the tip? Does everyone understand why that is? The vortex lattice method is actually a perfect example of the difference between these two. What this is representing, what this would give you is that this is saying that the lift is a constant tip to tip. There's no change. If you remember, lift is rho d gamma, and that can be sectional. This can be lift of y. So if lift of y is a constant, then gamma of y has to be constant, which means there can only be 2 vortices here. But we know that can't actually work because that would have huge pressure jump top to bottom over no space at all. Nature won't let that occur. So instead, what we get is that this is a continuous change of lift, which means a continuous change of gamma. And the way the vortex lattice method works, we'll take it out. Put a marker there. Meaning, let's say we have two panels. Control point, color, like down circulation, trailing vortices. This one gets that direction. This one gets the other direction. And these two are, this is the tip. This one's going to have less lift than this, right? Because it's on its way to dropping to zero lift at the tip. And so this is exactly what you're constructing inside of the BLM method. And so this is gamma 1, 2, and these two, they're actually exactly on top of each other. So they partially cancel each other out, right? So the net change here, the net strength of this is gamma 1. That's really the delta gamma. So this is the discrete form. In real life, you would increase this to infinite number of infinitesimal panels. This would be a continuous thing. And now you have a continuous shedding of vorticity out to the tip. The tip gets the strongest one because if you look at the lift distribution along the span, it gets quite steep up there. This is the CL Y. When that gets steep, gamma, the local gamma of Y gets strong. And so that by far the strongest is usually at the tip, unless they have some weird tip work, like a washout wingtip, huge taper or something like that. Usually it's maximum out there. And then what happens in real life is that these tend to kind of all get swept up into one giant vortex. Saw some images of that. If you go downstream a little bit, everything kind of coalesces to one. So they're all kind of in the same orientation on that one side. Anyway, so that's what the BLM method is doing. So you'll see, take your code and you start pumping up the number of panels. You'll see the lift distribution will change, but asymptotically it should reach something that's basically the same. Usually the biggest problem's out at the tip, again, because it's super steep. So if that first panel is here, then the gamma you get is maybe up here someplace. Really want it to be going down there. So the smaller you get the panels out of the tip, the closer you'll actually get to the lift at the wingtip. You'll never quite get there because you're measuring it at the center of the panel, which is never quite at the tip. All right. Anyway, that's subsonic incompressible flow, potential flow. As long as we're looking at that, what do you think happens in supersonic flow? Nobody does straight wings except maybe Bell X1. Say I have a straight wing. What do you think the lift distribution looks like on that? We get this? Yeah, you can't. If the reason we got this is because the effect of that wingtip in subsonic flow reaches everything. It reaches the entire span. But in supersonic flow, disturbances are contained, right? If this is my wingtip, this is the first bit of noise at that wingtip, it's contained inside this cone, right? That cone has the slope equals sine inverse 1 over Mach. And so the wingtip can only affect this little chunk of wingtip. Everything in the middle can't see the effect of that wingtip in supersonic. Again, nobody's gonna make a straight wing supersonic flow because you'd never get through Mach 1 probably. It would be very challenging. But anyway, some of the differences between subsonic and supersonic, the way disturbances propagate. This really plays a huge role in some of the aero that we do on missiles. Start getting to highly swept wings. They're actually, they become extremely forgiving supersonic flow, both in terms of getting solutions and CFX, forgiving, and also in real life. And there's one other thing. These are last little bits out of Platzer's chapter 4. I think the last thing is this Prandtl-Glauert transformation. So we look at subsonic. We had that equation. It's what, 1 minus m squared. Zero. That disturbance potential equation. And so what they proposed was I could do a coordinate transformation, like stretch coordinates. And so if I use a transformation where I have x prime not being the derivative, but being an alternate coordinate system, x per root 1 minus squared y prime equals y. If I apply that to this, then I can recover, what will happen is I'll recover exactly dxx plus dyy equals 0, incompressible version of the potential equation. And further, if you go through all of the math that we did for everything else, you'll find that you can use this transformation to just modify the coefficients that we get. So CP equals CP prime over root 1 minus 30 squared PL equals L prime over 1 minus 30 squared, so forth. You do that with all of the parameters, and it's kind of cool because now you can go back to everything you know for incompressible flow, and by just applying this transformation, you can get. It's not perfect. It's perfect within the realm of this kind of linearized approach, but you can get good estimates of the performance of a wing. Just applying that. So anyway, kind of useful. It's really kind of like stretching space in one direction in order to take away the compressible aspect of it. All right, so let's actually go back and let's share screen here. Let's take a look at homework 5. I guess before I go on, anybody have any other questions on homework assignment 4? Yeah.
Did you figure out about the sign change?
I forgot. I'll try to take a look after class and email everybody. I seem to recall there was a sign change we had to do that was different from the book, and I think the student online had the right thing. I think it's due to the fact that all the DXs have the opposite sign. Because I had never put enough thought into it. Anyway. Right. So let's see here. We have homework 5. Let's gouge up. So I'm going to do some things that are a little bit different from the gouge, only because the gouge is maybe a little bit stale, and there's some shortcuts we can do to make your life a little easier. But the few things that we'll have to remember, we do still need. We need the 6672 pascals and the temperature of 70.15. And I don't know how many people have gone through this yet, but this was kind of a fudged number. It's unmeasured. We didn't have a way to measure it in the tunnel. And so this was kind of a hack, and then a bunch of iterations to try to achieve Mach 4. And if anyone's done it, turns out we don't quite get Mach 4. I'm sure it's good enough. It's out to like 4 decimal points. But anyway, knowing how to use expressions, we can actually eliminate that whole guesswork bit. So we'll do that. So let's bring up SolidWorks. I think I probably already have a geometry. Oh, and actually this reminds me of another question that came up. Maybe we can take this moment for clarification. So yeah, for the purpose of this class, I made the domain super short because I only care about the surface pressures and I don't want to wait for it to run with a bigger mesh. But it's kind of fun to stretch it a bit, see all the craziness that happens downstream, if you don't mind spending a little more computational time. So what do we got? We got a chord length of 100 millimeters, half thickness of 3.25 millimeters. And then the way I generated this, I attached the airfoil to a chord line, which I can move any angle I want. But if I type something in, then degree, I get whatever I want. And so when it comes to, somebody was confused on how we do the Prandtl-Meyer expansion on the VT calculator for this. It was somebody DL, and it was when I got to switch back to the whiteboard when we had a discussion. So maybe everyone in class got it. Does everyone know exactly how we got the angle for this first base? There, it was, you can actually dimension it here. Let's see, it's going to be this. That's our half wedge angle. So that's the wedge angle of the airfoil itself, and then we subtract 1, so 2.719, I guess it was. And then the question came, how do we get this? And this is a point that's different for the VT calculator than it is for the perturbation theory. You want to remember what the difference is between the two? So you've got, make it look bigger than it actually is. My 1 degree, my airfoil, and this is my 3.719 degrees. So when we get back to here, what did we have to do in the VT calculator? We had a Mach number here. We solved something like 3.8, I think. What's that? To get from here to here, yeah, that does everyone understand where that came from? Figure this out. So this, they're both the same as this. So whatever our Prandtl-Meyer function is here, this one, 2 is omega 1 plus 2 times theta. Does that make sense? Everyone got that? I think I had sketched this on the board, but poor guys online, I forgot to show it to them. And if I guess if it wasn't symmetric, then 2 betas might not be the same. But anyway, understands it's the delta change in angle that matters. I don't care what free stream angle is. But how do I get omega 1? Yeah, that's where you go to the isotropic thing, and there was some reference for not 0 or 1. This is an imaginary surface, and it's the unwrapping from here to here that gave us the Mach 3.8. Yeah, so that gave us, I don't know what it was. plus some decimal points. I think the sum of these two is just over 70. So what's different when we apply the perturbation theory? Yeah, we don't care about the delta here. Every surface knows nothing about any other surface. So it's really just this angle with respect to free stream, this angle with respect to free stream. Draw it maybe a little bit better here. A little closer. My free stream. This is 1, 3. So let's generically call it alpha and theta. So what's the angle of that surface for perturbation theory? So to reach alpha, it's bending away from the flow, right? So it's a minus alpha, but the theta is bending into it. So this angle is going to be theta minus alpha, right? And then here's theta. This one has minus alpha and the minus theta. And then on the bottom, the thetas are the same, but the alphas change. Plus alpha and minus theta. That's right. The alpha is actually bending into the flow. Here, the theta is also bending into the flow. Here, right, close. Anyway, I think that's right. So anyway, just the angle convention is different between the two approaches. A little bit of effort to keep track of what's going on. All right, let's go back to sharing. All right, so anyway, that's my geometry. Let's go and get out. I think it's already saved. Let's save it again just in case. And let's start up ANSYS here. Incidentally, for anybody who did a personal copy of SolidWorks and tried changing to Neptune when Jupyter went down, I think you have to be using Jupyter for the new version of the up switchback. So let's see effects, order geometry. Sure. You guys are welcome to play around with some of the mesh settings. I threw in some numbers that kind of work. I'll tell you some things that maybe don't work as well while we're in there, but the goal is to try to get the surface pressures as close as possible. For if you're interested in pretty pictures, then we'll use this mesh refinement capability that starts packing more cells in wherever there's steep gradients in the flow. It doesn't make quite as much difference on the surface pressures, probably affects the moment a little bit. So let's name some stuff here. Started. 1. 2. Up. gonna go ahead and call it outlet because it'll never be anything else. Let's and then I don't know if anyone's ever tried this, but I want to take all the airfoil ones and turn it into another named entity. So I'm going to hide all of these and then grab this box select tool and just sweep it out, and anything that is left it highlights. And now I can call that, oops, one. Uh, it's not giving me the name. Click what? Is there a shortcut? For now and then it does this. Why? Shoot. And I occasionally get it to trip out, and I've never found the correlation for an action to oh my God. Maybe it was where I was focused. Right. Got these little nuances that are hard to figure out. But after all that, I'm actually going to name the individuals, only because it's useful for calculations later. So call this one base one, two, base three. Right. So everything's named. And then we want to do a sweep method again because we want to minimize our effort on meshing. Um, Unfortunately, when you do the mesh refinement, it ignores that. If anyone in here is trying to use Fluent for this, I don't know if they do the mesh refinement. I think they do, and then it shouldn't be a problem because you can actually do it literal 2D solution. Fluent. So maybe this is one I should move to Fluent at some point. So let's see. Insert method, volume, sweep. Target. Oh, again, my bad. select things you can't see. For all quad, get it in one cell. And then we just do want to do a couple of things here. Let's set the, and turn off a few things. Let's turn off curvature capture. Shouldn't do anything anyway, but I want it. Don't want any featuring. On this problem, it never causes grief, but on some of the other problems we do, it might. And then let's set size, I think, to 2 millimeters. Seems to work pretty well without costing a lot. And then when we solve this, all of the interesting action is going to happen right at the all the vertices, really, right? That's where shocks attach, and that's where the expansion fan attaches. We'd kind of like to help it a little bit there. So let's add some sizing. Vertex. That point. Y. So it's going to do a sphere, and we just want it to be the one point and let it taper off around there. So I think I did 1e minus 4. And you're welcome to play with smaller stuff here. It doesn't seem to help. In fact, it seems like the solution gets worse if you get too aggressive, making these things tiny. But feel free to play around. Unfortunately, sphere of influence is one where you can't grab more than one vertex. So you have to actually recreate this for each one. But they do have a duplicate feature. So in there, all we have to really do is select this one. Duplicate again. Saves a little bit of time. Unfortunately, each one of them, we're copying the sizes, but if you want to just change the sizes all over, you have to go in and edit each one of these. Oh, it should be good to generate. It should be really tiny. Oh, I think if you do it the nominal length, it's like 23,000. I think I've gone up to like maybe a meter downstream. The main punishment when you make it long is when you start to do the refined mesh. You need to have a lot of points at the end. So it gets progressively slower and slower and slower to compute. All right, so that should be good. I've tried packing a man along the surface here, and again, doesn't really seem to help. But I don't know, fiddle with it. Maybe you can find a sweet spot where the cost benefit ratio is the best. All right, so let's close that. Incidentally, I don't know if anyone's done this, but let's say I was working here and then I decided I wanted a longer or a shorter domain, or I wanted to change the angle of attack. You can actually go back into SolidWorks, make your edits, save it. And you can come back in here. So you can try this, update geometry from source. So if I wanted to say go to 2-degree angle attack or 5-degree angle attack, I could change it in SolidWorks, save it, read it back in, and all of these names stay the same because I didn't change any surfaces. I just moved things. And so you don't have to redo any of these assignments here. They'll all be set. They'll just bring in the new geometry, you mesh, and done. Sometimes you end up with a ton of these like sizing things. And if you have to reduplicate those each time, it's just a horrible exercise. Anyway, nice little shortcut. Great. I should probably save this thing. So the first thing to do is to go ahead and set up the equations that we need to solve. Let's go in here. When we went from incompressible to compressible, remember in incompressible, all we needed were the momentum equations and continuity, and we had closure. But when we go to incompressible, we throw in rho is now a variable, and so we have 4 equations and 5 unknowns. We're in trouble. So what do you have to do? You need a couple more equations, right? So one, we'll throw in the energy equation. It's actually done over here. Energy, 1. And then what's the other equation? Because total energy gives you one more equation, but it also throws in temperature. So now we have an additional unknown. We need an additional equation. What's that last equation? Is that? Edit here. You don't have one volunteer. So this was the heat equation or energy equation they call it. So that brings in, it's a huge equation actually. It's quite a painful one to solve. But it brings in a relationship between all the velocities, density, pressure, and temperature. So now since we've thrown temperature in the mix, we now have 6 unknowns and only 5 equations. Not entropy, but not entropy. Yeah, no, I mean, you can compute enthalpy from anything in here, but it doesn't give us the equation we want. It's the ideal gas law, right? Or P equals rho RT. And that comes from here. They do it in kind of a weird way. When they say air at 25 C, that means rho is a constant. It's not changing. What we want is air ideal gas. And that lets it actually throw in the ideal gas equation. So yeah, that's the way to do it. Another thing we want to do, since we're comparing this to a wind tunnel experiment where we actually have an absolute pressure measurement, we need our reference pressure to be absolute. This comes of pascals, 0 is our reference. Okay, and then in this case, because the body is super clean, we don't have any like backwards facing steps. We're not going to have any separation, so we can probably get away with assuming that it's laminar. I think you get about the same data if you use a turbulence model. It'll just cost you more. If we actually had like the backside of a missile or something where you have a separated region, laminar is going to fail miserably. So then you definitely want to have turbulence. Anyway, in this case, I think we can get away with this. Makes it go quicker. All right. I think that's everything there. And I guess we can start doing boundaries. Oh, let's do some expressions. So we don't want to have to guess at that velocity. So let's figure out how to calculate it. So let's do a few things. We want to have, we actually want to calculate, we want to be able to put in the Mach number and calculate the velocity from that. So to do that, we need to know the local speed of sound, which is gamma RT. And so that means we need gamma and R. It turns out, they don't tell you what gamma and R is. They treat them as variables. But if you remember, gamma and R come from specific heats. So we can kind of force it to do what we want. So let's call C pressure, or coefficient of heat, constant pressure. And the equation we'll use, we can go ahead and build it here. Say it's the area average. We want variable will be, find it here, be the specific capacity, constant pressure, one I don't want to type in, at the inlet. The other ball average. Constant volume, inlet. You could try to type in the values that you think you know, but I'll tell you it's not the values that they have for gamma NR, or for these for that matter. They do carry these out to quite a few decimals. They don't give you quite the gamma NR that you're used to. So now we can calculate those. We'll have R gas will be, what was it, CP minus CV? CS minus vol. And what, gamma. Ratio, C press over C vol. And then we need a few other things. So let's define constants. We have T infinity, which is given. Was what, 70.1, was it 555 K, I think, something like that. Oh, and I think it's finicky about the case of K. I think if you use a lowercase k, it rebels. So, and then let's go and put all our constants in. We have P infinity was what, 6722? Is that right?
Yes.
Yeah, pascals. And what else? Now we can throw in our speed of sound infinity, which is square root of gamma times R gas times T infinity. And our Mach number, so our other input, U infinity. Oh, okay, good. Yeah, thanks. What was I going to do here? Well, Mach number 4. 6672. All right, and so now finally we can get U infinity. So it's going to be Mach infinity times A infinity. All right, what else? So we're going to want to compute pressures on the surface, so we can do that integration. You can go ahead and throw that in, I guess. We can do, it's called P1 is equal to, this will be the area average of pressure at the inlet, or I'm sorry, at phase 1. That, oh, I forgot this doesn't actually help us here. Too many steps to fix it. You want go away. Three. Three. And lastly, 4. Oh, shoot. Oh yeah, One here, copy. 4. All right, we can also do pressure coefficients in here, and there's a kind of a handy shortcut we can take. Share. What's the equation for CP? Infinity pressure. And we haven't computed that. That's normally you. We're used to that being. So we could compute rho infinity, I guess. Go up to the inlet and do that. But there's a little manipulation you can do. You have rho equals over R2. And then we also have a squared equals gamma RT. So that gives us a gamma up here, and it becomes a squared. We can plug that in, so we get half gamma infinity walk squared. And we already have all of those, so we'll just use that. So let's add. Okay. Expression QInf 0.5 times E infinity squared. Finally, my pressure coefficient. Oops. It's equal to pressure minus PInf over QInf. And the only reason to really do that here is because it makes it easier for you to compare against perturbation theory. All right, I think that's it for expressions. So let's do some boundaries. Easy ones. Symmetry. To oh, it's going to be the top and the bottom. Make it free slip. 20 boundary layers. Well. Also wall. Also free slip. And outlet. So as you say supersonic, nothing else to do. Anything downstream can't affect you anywhere upstream. And then lastly, let's finish this last one. Break. Inlet. Sonic. And we want normal speed and pressure. expression, P infinity, normal speed, expression, infinity. Pressure is also an expression, T infinity. All right. Something else. Good. I think that's all our boundary conditions. So let's take like a 5-minute break, 10-minute break. Come back to that. Yeah. So you could run it turbulent, but then there's a couple of problems. If you have turbulent flow, then you really want an inflation layer. But I think the inflation layer is incompatible with the mesh refinement, so it couldn't use the mesh refinement. I think that's a true statement. It's not going to, the boundary layer is going to be so thin. Technically, it'll change the shock angle a little bit, but I think it's kind of lost in noise. You can try it if you want. You have to really pack in some cells, so the inflation layer is going to be ridiculously thin. So the cost of the calculation is going to be high. You can skip a transition, probably, because the transition is like the first cell. Some of it's going to be, actually, maybe the most not that high, because we're flying at the upper atmosphere.
But that's why we.
Yeah, anyway, we skip it just because the calculation underpins. Yeah, because those tiny cells would make the ridiculously tiny. They technically would alter the solution slightly. And then, if you're trying to be precise, then we probably like to carry the calculations up in front of the nozzle, the throat. And so start with subsonic and go through throat to turn supersonic, because the boundary layer is already growing back there. So I don't know. Yeah, it can be done, but for its purposes. In fact, the next two simulations are also supersonic W3 problems. Will ignore the bracelet there. And we're only interested in the surface pressures, and then boundary layer is not going to make any difference there. Or like, maybe in like a series doesn't matter.
In industry,
Again, it depends. If you're doing like if you actually wanted to, you're doing like a missile design study, you cared about drag, yes, it'll be in there. There'd be no way to skip it. If you were trying to do like the control derivatives, like the effect of like pitching moment on the deflection of control source on pitching moment, you could skip it because those are all based. So usually those are, in fact, a lot of those are actually potential flow or VLM methods, because they get you close enough. It's really only when drag or if separation is a possibility, but you'll find in supersonic flow separation is less of a problem as well. The flow just doesn't want to separate. So yeah, it becomes quite interesting. I think it's the last probably do is a 3D version of this basically. And you'll do it in angles attack and both subsonic and supersonic. And it's both subsonic and supersonic, it doesn't want to really separate for two completely different reasons. The reason they use Kelly swept diamond airfoil canards on it. Just works really well. Yeah. Sweet. Looks about right.
I'm like, Federation.
Trying to get the geometry right. Yeah.
Every time I realize that stuff. Like, when I have curved wings.
Yeah. I think I've done it two different ways. For the quarter chord line, I almost always find the coordinates of the root point and the tip point. And then I just do like a run space between those two. And then on the back one, I used to find the coordinates again at the two endpoints. But the run space is way harder because it's center point.
Yeah.
So the other option is to, if you have an equation for the chord, local chord, then you just add chords to.
That's the biggest problem I have. I could do this really easily.
Yeah.
Give it some time in the suite. But once you add it into their taper ratio,
Yeah.
it
Always
is.
messing up your
Yeah,
equation.
the fact it's a linear taper ratio is kind of the, like, basically, I consolidated it into capacity control, just the first bar, and then you have the shift from the taper ratio. You have the shift from the suite. You can add those.
Okay.
It's like, I did it like, it's called elementary flow.
You're summing up.
Add it all together and it gets you your point.
Superposition.
Yeah, I superposition for the doubles, and it gave me all my points.
Whatever works. But that's why I try to convince everyone to graph it.
Yeah.
Because if you don't plot it, you have no idea.
The amount of just like one equals X plus B that I had done. I was just like all the different. This equals this equals that ain't. Yeah, this person. It's real. This was like, I'm gonna work on this all weekend. Like 2 weekends in a row, I'm doing school now. Getting closer to the end.
Well, makes you feel any better. I'll be in here grading all weekends. Way behind on grading. So try to get you guys 2 and 3 back. Sweet.
I'd be looking at it on.
All right, let's everyone back. Let's see. So what else we gotta do here? We've got all the boundary conditions. We've got our flow set up. We're almost there. Let's add some output so we can actually see what's going on in those pressures on the surfaces. Monitor this. I call it. Can't remember. I don't think I can use PU1. So press 1. Expression. My P1. Let's do. These don't actually change very much. Maybe I'll just stop at the first 2. All right. Is that done? And then let's go into solver control. We don't have to do a lot here. Let's so we're going to use the mesh refinement. That's this thing up here. The trick is what it does is we'll pick a variable that has some gradient we want to cluster points around. So density turns out to work great. The thing is, the way it does is it sort of subdivides cells, like cuts them in half or quarters. And once it adds new cells, it's very reluctant to give them up if they turned out to be in the wrong space. So I don't want to do any refinement until I at least have a pretty good stab at where the sharp gradients are going to be. So what I like to do usually is go ahead and run a bunch of stuff front to get me headed in the right direction. And then we'll come back and we'll add the mesh refinement afterwards. Again, let's make this something unobtainable. Actually, I think it can get to 10e minus 9. Since we're laminar and supersonic, it actually converges incredibly well. Let's see, I think that's it in here. So we should be able to just save it. Go. I didn't forget anything. Figure out here. Oh. It's gonna be pretty fast. Fast after partitions. All right, so now we have our mass momentum. Note W momentum is not showing up because we have sweep method. Heat transfer for the energy equation. And then here's our pressures. We get some crazy spikes at the beginning, kind of settle out. And maybe change this to most recent. These are actually converging right off the screen. Change those. Change the number on. And save it. Get out. Let's have a look. Yep. Let's have a look at that block. All right, looks pretty good. But show the mesh. Our mesh is kind of cruddy. And the shock typically gets smeared over about like 3 to 4 cells. The code is a little bit cracked. We haven't really talked about, well, we talked really briefly. Remember the term upwinding when we first introduced the idea of those the characteristics, and we said you can't use the information outside of these two characteristics to influence point. So they did this upwinding thing, and so they switched to upwinding when they get right around the shock, which lowers the order of the calculation a little bit. Everywhere else, they're using some kind of higher order scheme. So anyway, the shock is super smeared because the cells are big. But let's go ahead and create our surface pressure plot. So we have to first create our contour on the airfoil. E3 polyline. Contour. And now we can create a chart. Line X. Y will be freon pressure. So it should be constant pressure on those faces, but it's not. It's messy because we get all these like ripples. And you know, Gibbs phenomenon is when you have a discontinuity in a solution and you try to numerically move across it, you get these crazy oscillations. So here's the oscillations, and it just takes a long time to damp out. It doesn't really have a chance because the cells are so big. But interestingly, We go back here to our expressions. Let's just look at the values. 87.15. I think 87.22 is the exact answer. So we're already within 1%. Pressure 2. Yeah, that was 40.58. So we're right there. So you could stop here if all you cared about was the average pressure on the surface. The flow isn't all that accurate because we would expect these things to be straight lines. So that's what you're going to try to accomplish with the rest of it. So let's minimize that. Let's go back into pre. And now let's add grid refinement. So we want to choose a variable that we're going to look at gradients on. So anything that has a big change, does anyone remember what the absolute pressure was across the shock? P1 to P2, does anyone remember what that was on the calculator? It wasn't very big. It was like 0.998. So that'd be a horrible one to choose. Mach's okay. I think density is one of the biggest you get. So I'm going to choose that. And then you got a bunch of stuff to fiddle with here. And I'll tell you, because of the problem of it, if it throws down cells in places where eventually there's not going to be sharp gradients, it doesn't want to get rid of them later. So you're trying to not add points until you absolutely have to. So we want to tweak stuff in here to minimize the chance of that. So one way to do it is to crank up the number of times that you refine the mesh and then reduce that. What that basically does is I'm gonna give it a total number here. I'll do like 120,000. So my domain is tiny. What it's going to do is it's going to take the initial number and the final number, and it's going to basically divide it up into, actually we do a cut down on time. It's going to divide it into 8 segments, and it's going to try to make sure that each time it refines, you're going to have that number of cells in the thing. So it turns out if you add them in small increments, it does a better job of putting them in the right places. At least that's been my experience. The other thing you want to do is that each time it refines it, then it's going to run the solution for a bit. And so you'll start to see it reconverge after it makes all these changes. And so you can fiddle with these to decide how many iterations it does between steps. For your particular case, I've had the best luck with 70 and I think 5, maybe -6. But I think for this problem, it actually doesn't need 70 in most cases. So it'll stop early. So that should be good. Oh, I forgot to do one other thing before, but I think we can turn it on now. So that's good. Let's write it. Start this back up. I forgot to turn on double precision, and that actually helps quite a bit here. I think we can turn it on after the fact. It turns out when it does the, every time it remeshes, it has to interpolate the old solution onto the new mesh, and it actually does that in single precision. This won't make too much difference, I think. And let's make sure we're starting from the current station. The first thing it's going to do is going to load in the old solution, and it's going to immediately redo the mesh. And we'll immediately see W momentum show up since it's now, it's got multiple cells in the third direction. I'll tell you, this tool works okay in 2D. We're going to do some 3D problems, and it's not awesome in 3D. Yeah. I'd say there's other ways that you can get better results in 3D. All right. So there's our first remeshing. Disturbance, yeah.
Too much cells in the third direction.
Because it doesn't honor sweep when where it remeshes. And what it tries to do is if it makes the cells small in the XY direction, then it's going to also try to make them equally small in the Z direction. I've tried to make the sliver of the domain tiny, but it doesn't actually end up giving you better results. One is the cells are all smaller, so the DT gets smaller. And I can't seem to get it to converge as well as I get with the 1 millimeter thick domain. Again, you're welcome to play around. There might be a slightly better sweet spot. All of those things you can tweak. This one works pretty well. One thing you might notice here at each time step, it's telling you the highest Mach number that you get. If you start to do really complicated 3D problems, if they go unstable, this is where you'll see it first. This number will start going crazy. You'll see numbers in the like tens of thousands of Mach showing up. And that's an indicator that the next time step or two, your solution is gonna fail. It's a good idea if you see that happening to hit stop, because then you can actually look at the results and you can probably figure out where it's going bad. Once it crashes, you don't get results. And so then you have to rerun and stop it. Right. Okay, there was our second refinement. I don't know if we'll wait for all of these to finish. Let it go a little bit. Yeah.
So when you're refining the mesh,
It does it automatically.
it seems like you're never going to reach convergence.
So what it'll do, it's going to do 8 of these refinements, going for a target of like what I put in was 120,000 total points. It's going to shoot for that. This looks like it's getting really slow, so I'm curious if I missed. I think I screwed up on. That looks okay. I guess it seems slower than it should be. I've got something else going. So once it's done with the 8, then it's going to drive. I think I had it set up for 150 for the initial thing, so it's going to do 150 at the trailing end once it's done to try to reach convergence. You can try to get it more converged in here. It's that's kind of where you can play around a little bit with that 70 iterations and the 5 u minus 6. They're determining basically the cutoff point. And you don't want to converge too much because then you're kind of wasting time. When the residual gets super small, you're not really moving the shock and stuff much anymore. You're just getting rid of a little bit of noise in the stuff. And all you really care about is where's the shock, where's the expansion fan, because that's where you're going to pack new cells on. So you want to get enough that they're as focused as you can get, but there's like a diminishing gain. You drive it further. $27,000, 66,000 nodes.
Special methods to mesh.
Yeah, we'll see what it looks like when it's done. The mesh looks a little bit weird. It literally subdivides the cells. I did something like this. Oh, but we'll stop sharing while this is calculating. We're gonna do. It's the next homework assignment. Gotta go back and look. 2 more homework assignments. And one of them is this thing called a wave rider. Anyone heard of a wave rider? Yeah. Wow. Oh, okay. So, so that was my thesis topic, actually. In the late 80s and early 90s, wave riders were like the hot topic in supersonic flow. Not for missiles. Nobody had a clue that they'd be interesting for missiles. Concorde was still flying, and everyone thought the next step is now going to be a hypersonic transport version of Concorde. And so everyone's looking into ways of coming up with optimal hypersonic bodies. And oddly, back in like the 60s or 70s, this British guy, who's actually not even an aero guy, he was a thermal guy. And he was trying to compete sharp bodies against blunt bodies for reentry. We were starting to try to fly to the moon. And so, classically, we have these capsules, blunt body, it's this huge bow shock. It's fairly significant separation, but it's an incredibly strong shock. Coming in at like Mach 25. So it's ridiculously huge temperature change across here. So we have all that insulation here, plate of materials. And so he had this idea, well, how does that compare to something that's sharp? I have some like those. Now I've got a shock that's basically attached. Maybe look close enough, there's some little valve shock section of it. So he wanted to do like a thermal study on this. And so he came up with this idea, how can I make the simplest hypersonic geometry that will create kind of an analytic solution so I can compute heat conduction inside this body? What he came up with, we take, say I've got a wedge. Reconnect. 3D version of a wedge, theta, arc. And so we're going to get bow shock comes off of this. But it's 2D, just stretched, extruded. So the flow under here, it's all constant value, right? Streamline that comes in, streamline gets in, parallel to the surface. Here we have Mach infinity on here, Mach 1 pressure. Everything's like they're fixed. They're just like you've been doing with the Pascal calculator. So that's, you could imagine if you had a finite span of that, let's say you have some unobtainable material and make an infinitely thin unit on here, the shock is going to be contained in the flow outside of the undisturbed. So in some sense, that's now a 3D aircraft, right? It's flying in supersonic flow, and the shock is contained between this type of so now I can use pressure on the bottom. And so what he did, he got a little craftier, and let's say that this shock was generated by an imaginary wedge. And so if I go upstream, or let's say even on the back plane, if I draw some shape like this, and then I look at all the streamlines that go through all this flow upstream, pass through this line, all these parallel lines, and they go up to go until they hit the shock. So basically, say like this. Bad job of drawing it. Call it carrot one writer. You can actually calculate this. So this is one top surface. Usually for simplicity, we just make it parallel to the free stream, so no disturbance at all. And then the bottom, got the shock. It's contained, touches the leading edge on both sides. And this flat plate here. So this is like the simplest wave rider you can possibly have. They call it a carrot wing wave rider because it's just a keyboard thing to carrot. The guy who invented it's called, his name was Terrence Nonweiler. I actually went to a wave rider conference back when wave riders were popular enough that we had a whole conference dedicated to wave riders. And a guy came and presented a paper where he called it a non-wave rider. Terrence Nonweiler was actually there. He was fascinated because he only invented this shape because it was an interesting analytic way to study heat conduction inside this thing. And he had no clue that people would actually think this was somehow an ideal shape. And it was a little bizarre at the time. I think everyone had this big idea because the shock touches the leading edge. That means there's no flow that spills around the leading edge. So kind of like we were just talking about the difference between subsonic and supersonic, tip vortices travel everywhere in subsonic flow. this would somehow isolate the two, so no pressure spillage. And they thought somehow that made the shape optimal in some way. When I was a student, I started working with a researcher at NASA Langley, and then he was doing not this simple planar shock wave rider, but these conical shock wave riders in the unitary plane wind tunnel. He had a Mach 4 and a Mach 6 version. And he actually got kind of crafty. He said he's going to look and see, are these shapes actually better? So he took some of these shapes and tested them at all different angles of attack. And then he also took the same thickness distribution but mashed it so the top was flat. So it had the same area distribution, but a shape that was clearly not a wave rider. There's no way that shock is going to be attached to the tip of the nose. And he ran that at all different angles of attack. And it turns out the one that was mashed flat actually did just the tiniest bit better. And even the one that was the regular wave rider, the best L over D, turned out to not be at the point design. It is a point design. If I change the angle of attack of this, that shock is no longer going to be where I thought it was. I developed the shape by knowing what the flow looked like. But as soon as I change the angle of attack, normally that would mean that the shock angle would change and have to come with the body. So this body, suddenly the shock is going to either get squished up the side or get thrown out. And then the flow properties are all going to be variable in there. It becomes a messier thing to solve it. Anyways, it's sort of a point. Anyway, that was all the rage for a while. The design technique we call it sort of an inverse design. You start by knowing what the flow looks like. And then what you do is you plot the way streamlines go through it. And then, much like we've been discussing with potential flow, a streamline for inviscid flow, a streamline can be a body, right? Can represent a body. So now I have this whole family of streamlines that have figured that's the lower surface. Right? To get more elaborate, instead of a wedge, making it a cone that generates a conical shock. Same thing. You have streamlines that pass through there. They're not straight lines anymore. Gets a little more work. I did it by finding arbitrary shaped shocks, which is challenging because when you have 3D shapes, it's not always obvious what is a feasible shock. You could say I have a shock that's this shape, but it could be an impossible shape for a shock to ever be. And so it can be this weird solution. Yeah, this is incidentally one other thing we can point out here. What we're doing in CFX right now is what we call a shock capturing code. Before we get started, we have no idea where that shock is. We're using CFX to show us where the shock is. In this case, I know exactly where that shock is, and so I actually start my solution. I don't even have a domain outside of that shock. The shock is my boundary, and I would use the shock jump relations like from the Beacon calculator. That would be my post shock condition, and then I would use that to calculate everything downstream. They call that a shock fitting program. It's great if you know where the shock is beforehand. It's a great way to do it. If you don't, choice. CFX. With this, in the old days, you could literally have an isentropic code here. You could apply a shock jump relation here. You could have an isentropic code back here, and the shock would be perfect. And any noise that would normally be created by trying to shock fit, seen in CFX, all that would be gone. So that's the closest you can get perfect. But again, only works for cases where you physically know where the shock is. Let's see. Let's go back to screen. See, 1, 2, 3, 4, 5, 6, 7, 8. So it's done. It's just going to finish convergence now. So it should go out to 150 here. And I don't know how close it'll get to 10 to the -9, but I think it's pretty close. Yeah.
You said ANSYS can't make a shock. or stuff like RPD.
So numerical methods can't. They don't.
But they can't like, they know like the pressure changes happen, and they can't like.
What-
They're like an average.
So when you use that Virginia Tech calculator, online calculator, that thing is treating the shock as if it's infinitely thin, and it's giving you an exact calculation for the pressure across here. This has none of that. It doesn't know any of the equations that are in that calculator. It doesn't know. It's solving Navier-Stokes, and it just happens that the shock falls out of the Navier-Stokes equations. But when you do these finite difference or finite volume methods, they always are going to smear. They can't do a discrete change. They're always going to smear stuff out. In real life, actually, it's not infinitely thin as well, but it's at sea level. It's yeah, it's like 15 free mean paths or something like that.
Sure.
So it's microns down here. But by the time you get up to the top of the atmosphere, then it's in low Earth orbit, it's like a couple of kilometers. So I mean, there's no air, but it's very thick. For reentry vehicles, it can be quite thick. Yeah. It's some variation going on in there, I guess. I never looked at it. They quit using, so that it becomes kind of another area of aerodynamics for rarefied flows. So if you're into reentry vehicles, you quit using Navier-Stokes and you start using Monte Carlo methods. So you literally treat molecules as individual particles, do probability studies of impacts particles. Yeah, but up to the height of like a U2 or a SR-71 or something, this is good. All the way down. And so people tried using the stop on this. It almost always works. Occasionally it won't. And then you're just stuck. You have to wait to finish or you'll lose your results. It's kind of annoying. You can see these kind of quit changing very much. Let's quick. So interesting. This is slightly different than when I ran it earlier. Um, I didn't start the double precision right away, so apparently that actually makes a difference. The exact solution, I think, is 8722. So anyway, we're within 3 pascals out of 9,000. So is that like 0.3% or something? So not bad. Into our results. And there we go. So now we're actually getting pretty close. But notice these oscillations, these are bigger than they were before. So that's kind of the nature of it. The more you try to refine something that should be a discontinuity, the bigger these oscillations get. The numerical schemes actually try to throw in some things to try to cap that. Before they did it, you get big positive spikes, but you also get big negative spikes. And if you don't control this, the spikes can get big enough that you would actually get negative pressures, which is possible. And so the codes would just crash. So now they have these like TVD schemes, total variational diminishing schemes that try to limit how much these oscillations can be, just to make sure you don't go unstable. Okay, let's see. Start to viewer. And let's see if these actually improved at all. Yeah, 8719. So I think we're about the same as we were when we didn't refine the mesh. But now you can see we're actually doing a pretty good job of packing points in. If you drove it up even higher, you would see these get even better. Go back to off So a few other things you could potentially do in here. Oh, one thing I forgot to do before that you might want to do is come in and probe the flow. Oops. Yeah, so 4. And hopefully almost every place you go is 4. I think when you get way toward the exit, sometimes you starts to get a little off, but it's like the 5th decimal point, so not bad. And if you probe in here, you can see it's pretty constant, not exact, but not bad. And then if you look, you can see we're actually getting you can see that the oscillations here. You can see the Mach numbers actually getting lower in some places. You get this like echo through there. The more you pack it in, you'll actually get bigger amplitude oscillations, but confined to a smaller area. A few other things you could do in here. If you want to, for example, compare the angle of the shock calculation that you had in the PT calculator, you can come in and, for example, add a line. And let's see, this is a minus 0.05 about. And it ends at 0.6. And we're 1 degree. I forget what this is. It's like 0.082 or something like that. And then we have to guess at this one. 0.03 maybe. Let's see what that looks like. Get it. I don't know what it is. Calculated. And then what you'd want to do, this one, top one's actually harder than the bottom one because it's a little bit more spread out. Hunt for something that looks like it's pretty close to the edge. You could, it'll add a third dimension to it, but I guess you don't care here. Yeah, and then you would basically do trig on these numbers and find the angle. Yeah, anyway, so that's a good way to, if you want to try to compare the angle to what you get out of the PT calculator. There is, like I said, some uncertainty here because I don't know if I'm putting it exactly where the shock is. We can do another trick. Let's see, let's switch symmetry to density. And then let's look at the change we get across here. It's going between like 0.3 and 0.4 ish. 0.3 and so we can do an iso surface. You want density right tool. Right. Density. We'll do, let's see, it was 0.4, about like 0.38. Something that's kind of in between the high and low shock. Let's turn it off. So this surface is about in the middle of the shock. So you could use that, I guess, to help guide the line. When you do the wave writer problem, it's a great, you can actually do a really good job of throwing a surface on the shock there. I think what else? There's a few other things that are kind of interesting, maybe. Let's make a line up front. Oh, that's 0.06. Is it 0.05? 0.05. Let's do 21. Now let's do some streamlines. You Y towards color. Lock. It's a bit. So straight lines out front, straight lines behind the shock. And then curvy as we go through the expansion fan, and then straight again until they see another shock. So anyway, if you do a longer domain with more reflections, always see that. You can always tell where an expansion fan is because you get smooth changes. I think that's about it. I don't think there's anything else. You can go ahead and do the pressure coefficient in here, just like we did the pressures on the different faces. So if you want to export that to compare against the perturbation theory, you can do that. That's about it. Anybody have any questions on how many people have already finished this? Ready? You gonna go back and do it now with the concept? You can go in and actually look at it, the gamma that it gets. We actually have it, it's in the expressions. So what it gets gamma. Gamma is 1.40025, so it's close. That one's not the problem. R is a bigger problem. This is off a ways. What is it? 286.9, I think is what we usually use. So it's off a little bit. You can go back and plug that gamma into the VT calculator, but yeah, it'll show up in like a piece of a Pascal with pressure. The shock won't change enough to notice. Anyway, it's a little bit weird when you deal with CFX because some of the constants that it uses aren't quite the constants that you are used to. It's always a little bit of a battle to figure out what you should be using. All right, well, good. Because that's it for today. On Tuesday, we'll start into chapter 5, I guess. Start looking at some 3D phenomenon. High-speed flows. And I'll try to catch up on grading.